Thank you very much. So I'm Bruno Régaldo, a PhD student supervised by François Lurier, François Boulanger. I'm also working with Erwan, Stéphane Mallard, and others. And so is it? And so the idea of this talk is to link some cosmological issues we are facing that François presented yesterday with statistical tools we're developing to solve it, as Erwan just introduced it. So what people in cosmology want to do is to do some archaeology of the universe. And there is this really important signal, this first light of the universe, the cosmic microwave background, that we try to study. The issue is that it's a very old signal, and what we're observing is something which is polluted by the galactic signal we see on the right of this image. And so the galactic plane is in the middle of this image. And so in order to unveil the cosmic microwave background we see on the right, on the left of this image, you need to develop a really accurate statistical description of this galactic foreground. And so this is what this talk is about. So what are these galactic foregrounds? These are some emission of the interstellar medium. So I will give you an example of what we see when looking at the interstellar medium. So this is a region of the sky called Chameleon Musca, observed at 353 gigahertz. So at this frequency, what you see is a polarized thermal emission of dust. And you see that you have these filamentary patterns that you need to characterize from a statistical point of view. And so just a little background of what is the interstellar medium. So the interstellar medium is made of gas and dust. It's a magnetized turbulent fluid described by Navier-Stokes equations. So there is some gravitation. It's also an open system exchange in matter and energy with this environment. So it's a really complicated system, which leads to complicated statistics. So the maps of the interstellar medium are highly non-Gaussian. And so from a more concrete point of view, what we're interested in are the Stokes maps, which are a way to measure the polarized emission of the interstellar medium. So I maps are intensity maps, and Q and U maps are linear polarization maps. And so you can model the thermal emission of dust and establish some analytical formula of this I, Q, and U maps. And there are integration along the line of sight of some quantities that depends on the density of dust and on the local orientation of the magnetic field. So these are phi and gamma angles. So these are some examples of these Stokes maps, I, Q, and U, for a magneto-hydrodynamical simulation and an observation, which is Chameleon Musca. So you see these filamentary patterns, and you also see that these maps are correlated. So I, Q, and U maps that all depend on the same quantity, the density of dust and the local orientation of the magnetic field, have similar patterns, and we need to take that into account when statistically describing these fields. So these are the properties of our data. They are highly non-Gaussian, they are correlated, and there is a specific property concerning Q and U maps. They depend on a reference frame. Actually, when doing some polarization measurements, you first need to define a reference frame. And so Q and U quantities depend on this reference frame. These are the transformation rule of how these maps are transformed when rotating the reference frame of an angle phi. And you see that there is a natural variable in it, which is a complex polarization variable, Q plus IU. And the global phase of this complex variable has no physical meaning, as it depends on the reference frame we chose. So to describe these stocks maps from a statistical point of view, we'll choose a wavelet scattering transform representation for both a real valued I map and a complex valued Q plus IU map. So we won't take into account correlations between I and Q plus IU, but we'll work with a joint variable of Q and U with this complex variable Q plus IU. So I remind you the expression of the wavelet scattering transform of a complex field. So this transform depends on some wavelets defined by scales J and angle theta. There is also a Gaussian filter phi, which behaves like a windowing function. And so the WST coefficients are split into 3 layers. We first capture in the first layer the local averages of the field. In the second layer, we get an information that corresponds to the power spectrum of the field. And in the third layer, we capture an information bound to the couplings between scales. And so for this example of a Q and U maps from an MHD simulation, which are maps of 128 times 128 pixels, we have, for regular parameters of the WST, more than 1,000 WST coefficients. But as we're dealing with some specific physical fields, there must be some regularity in these WST coefficients. And actually, when we look at the angular dependency of these coefficients, we see that there are some regular patterns. So for a fixed scale, we see that there are simple patterns in the coefficient of the first layer. For some coefficient of the second layer, for given scales, we see that the angular function is really smooth. And so this is something we want to exploit in order to compress our statistical description. And so this is what the reduced WST description is about. And by fitting these angular dependencies, we end up with only 61 coefficients to describe this polarization map Q plus IU. And we see that we get almost all the information contained in the WST coefficients by superposing our fits and our WST coefficients. And to estimate how complex is the information we have captured, we are able to make synthesis of from these 61 coefficients. We are able to synthesize image, and we see that we managed to capture this filamentary pattern with these RWST coefficients. And what is also interesting is that we have generated Q and U maps that are correlated between them, because you see that this pattern of the Q on the Q map appears here on the U map. This one appears here. So there are some correlation in this map that we wanted to capture. We actually get here. And so the next step would be to work with use this RWST model for observations. But the issue is that the regularity we're seeing in MHD simulations is not the same with observations, because the noise pollutes small scales. We are dealing with observations that are not necessarily stationary, and we are lacking data, so it's complicated to have good estimates of WST coefficients. But the whole idea of this RWST representation is that it enforces this regularity in the WST coefficients. And it can help us to reduce this noise in observations or to have better estimates of the statistics of the ISM. So I'll finish with this conclusion. So we have extended this formalism, this reduced WST formalism, to complex polarization maps. And we're able to make synthesis of these Q plus IU maps, so Q and U maps that are correlated. And the model, the RWST model we're dealing with can help us to mitigate observational limitations. So, and also finish with the fact that we need to take into account some correlations between I and Q plus IU map. And this is not what we are doing for now. But so this will require some maybe more advanced tools, generalized wavelet scattering transform on vector maps, and this is the next step for that. Thank you very much.